Good evening, everyone, and welcome to webinar number 10 from Quantum London. I think we already have 25 people attending. This is great. And I will just take a couple of minutes to do a short introduction. Together with me, you have Paolo Cuomo, co-founder of Quantum London. And we are a community of curious people and enthusiasts, people that are trying to understand the business implications of Quantum London, apologies, of quantum technologies and quantum computing more in particular. So we run a number of events like webinars, as the one we're running tonight, where we bring in experts that help us unravel some of the questions we have around, the topic of how the quantum technologies and computing will impact our businesses. And we also run a number of more informal sessions, like a Stammtisch, which is a Q&A informal get-together, where we try to, explore a few of the topics and look again at events and the webinars we have run. And we also started recently a coding session, a group of people self-teaching on how to code on quantum computing. And stay with us, because there's we will do a recap towards the end of what's coming next. And also on the page you see there is references to our social media channels where you can find out more about all the events that we run. So for today, we talk again about quantum security. And as we all know, quantum computing will be a positive force in bringing us faster and more powerful algorithms. But it also poses a threat to security, in the sense that it's likely that those algorithms might be used to break cryptography. The good news is that in this run between the bad guys and the good guys, this race, there's a lot of good guys, like the speakers we have here tonight. They're both from ID Quantique, which is a global leader in quantum safe security and quantum sensing. And we will have Bruno Hattner and Jean-Sébastien Pejon, hopefully I pronounce it correctly, which will help us unravel and explore the quantum security topic. The event is being recorded, so if you, for any reason, have to drop, or if you want to share it further with someone who might be interested, it's been recorded and will be published in our social media channels. And very important, this is an interactive session, so we have a chart on the right-hand side of your screen where you can ask questions, and we will try and filter and ask the most interesting questions. We will also have a Q&A sessions towards the end, where you can ask some of those questions you might have. Yeah, that's me done. I will hand over swiftly to Bruno and Jean-Sébastien to talk to us about quantum versus quantum.
So hello everyone, that's a pleasure to be with you tonight. And thank you very much, Paolo and Emanuele, for the invitation and organization. So we'll start directly with an introduction on quantum technologies quickly. So you, as mentioned by Emanuele, probably your main focus is certainly around quantum computing. On our side, it's more quantum sensing and quantum security, which have the advantage to be certainly a bit more simple and a bit more mature, with practical implementation and examples. These three topics are, as you know, in the radar of the government. It's identified as a strategic technology with lots of funds in billions invested, both from private and public sectors. And we are certainly part of this race and this quantum revolution as ID Quantique. China is pushing us, is pushing many countries. They are clearly certainly ahead in some areas, and security is becoming a key area, a key topic for the data, which have more and more value to bring. On ID Quantique side, if we look a bit at the past, we have been we're celebrating this year the 20th century 20th anniversary, and we've seen clearly an acceleration in the evolution of the technology and the products. I will focus more on the last 2 years. We can notice in 2019 that SKT has applied QKD technology in their 5G network. For us, it was a major implementation with production, large-scale production implementation. And security is clearly one of the key elements also in mobile and 5G network. In 2020, the first large and mass market application of QRNG, so quantum randomness, where a chip, our chip was included in the first smartphone. So here it opens the door really to interesting applications, more user-oriented with apps. So here you see today there are 2 smartphone models that support our QRNG chip. We have the Samsung A Quantum, which is the rebranded name of the Galaxy A71, and also the Iris from Vinsmart. So I will show you a few examples of applications using the output provided by the chip. So the quantum decade has started, and why should enterprise care? So I won't list all breaches that appear on, unfortunately, for many companies, you know, some have even to stop working or stop their production. Here, the focus is more to say clearly data has value. It's making sense. It makes sense to protect your data and to encrypt the data to reduce also the impact of a given breach. So that's clearly an area where we are at ID Quantique, and we help our customers and enterprise governments to improve the security level of the encryption by improving key generation, by improving encryption. And it's certainly applicable to many fields. We have the chance at ID Quantique to have customers in different sectors. So, of course, depending on your sector, the use case can be different, but you will see we have the chance to participate and provide solutions to these different sectors. So I will hand over to Bruno Huttner now, that will explain you in more details which quantum principle we use in our products and in our solutions. Bruno, hand over to you if you want to share your screen.
So Jean-Sébastien, let me just a second. Yes, I take over from you. And I have my slideshow, yep.
Bruno, in the meantime, will the slides be available afterwards?
Oops, I think there is something going wrong with my sharing.
No, we see your first, the first slide.
Yeah, but I don't see the rest of, wait, it's gonna happen. Yep, okay, all right, so, sorry, yep, okay, here we are. Right, so what I wanted to, so the idea really now is to see why quantum will have an influence on data security. So the main thing when we start with is really to talk about the 2 sides of the quantum computer. If you're here with us today, you know obviously about the great opportunities you have with a quantum computer, that it will you will manage to do some calculation, some computation, which were deemed impossible with a classical computer. But unfortunately, at the same time, the very same power of the quantum computer can become a threat, and it's a threat actually for cybersecurity. So it's really a double-edged sword, if you want. And in order to understand that a bit better, let's go back a little bit to modern cryptography. Modern cryptography is based on two important ingredients. The first one is random keys. Whenever you do cryptography, you need keys. Keys will be random string of bits, which basically you will use in order to do something which nobody else can know. So we will go back to that a little bit later, but that's really the first thing you need. Randomness is really a very, very important element in the keys you will be using all the time in cryptography. The second element which you need is what I called here a bit loosely maybe hard mathematics. Hard mathematics means you got problems which you can try and solve with a computer, but you can solve the problem easily in one way and hard in the other way. And of course, I give you a very simple example which you all know. It's about factoring. If you got this large integer and you want to find out the factors, it's relatively easy from the factors to calculate the large integer. I mean, you can even do it by hand, but it's much, much harder to go the other side. And these kind of problems which are easy one way and hard the other way, will be used in cryptography to secure your data. Okay, and that's really the basis of cryptography. So let's start with randomness. How do you get this random stuff? It's not so easy actually to get truly random system, truly random numbers. One simple idea is to say, okay, let's try and get it from external noise. We have here, I show you possible trace. It looks really quite irregular. So from this, if it's coming from whatever you measure, and this is a result of a measurement, and you can say, okay, let's use that as a random source. Unfortunately, if you use external noise, something coming from outside of your system, it could have hidden irregularities, obviously, and it could also be manipulated. Maybe what you are seeing is not real randomness, but it's something which somebody is sending to you. Another thing is it's not always available. Sometimes you cannot find this something coming from outside. Let's say you're in the middle of a data center and it's very well protected from the world. So how do you get something from out? If you got Internet of Things, very small devices, how can these devices can get some random stuff coming from outside? So relying on external noise is not always the best solution. The other solution you have classically is to work with a system which is chaotic. Chaotic does not mean random, but it means that you cannot predict it for a long time. You start at a given point with your system, you let it evolve, and very quickly you cannot know where it's going. Okay, and that's really the idea behind chaos. A chaotic system will go somewhere which you cannot predict easily, but you can predict a little bit. You can predict how it moves on for a while, and then at some stage you lose it. The problem here, of course, is that if you are using better techniques, you may be able to predict a bit better, or much better actually, and we are working on something like that at this moment. In addition, once you improve your computers, you can obviously predict better, which means that the quantum computer itself may attack this kind of random systems. Therefore, relying on classical systems to create randomness is not a true, it's not risk-free. You can have risk doing some with this, and that's why we advocate using quantum, and I will come back to that in a moment. The other requirement to do cryptography is hard mathematics, and we went through this factorization. And what's happening here is that the quantum computer has changed something which we believed was very hard into something which is now becoming easy. And of course, you all know about Shor algorithm, which really started, I would say, more or less the whole field of quantum computing, because it really showed that there is something which in principle is hard to do with a classical computer and which is difficult to do, which is easy to do, with a quantum computer. And people have started to devise new algorithms. For Shor algorithm is really the one which is the most important for us because it will break a lot of cryptographic systems. There is another one called Grover algorithm, which will also break some kind of systems, but not completely. It means by increasing the size of the keys, you can still recover something which is difficult, let's say. Whereas with Shor, factoring has become easy. Easy means as easy to factorize as to make the multiplication. Okay, so that's really the impact of quantum algorithm. So what's at risk? What do these algorithms, what is the risk presented by these algorithms to us? Fortunately, not everything is lost. We still have several mathematical systems which we can rely upon, which we can use for cryptography. One is symmetric crypto, or called also secret key crypto, which the quantum computer does not manage to break. The other one is called hash-based function, which is used a lot for authentication and things like that. And this, again, by increasing the size of the functions of the data you use, you can still recover security. What the quantum computer does is breaking most of asymmetric cryptography because it is based on this very factoring. It's really all of current asymmetric crypto is based on factoring, which is broken by the quantum computer. So all the schemes which will rely on that are not safe, will not be safe in the future. The future is when there is a quantum computer, obviously. Okay?
No, effectively, this is a question we often have. When do we think the quantum computer will be powerful enough to run Shor algorithm, for example?
And that's a good question. I think if I could answer that clearly, I would be quite happy. Most people believe that, I mean, looking at past progress, and we've seen a lot of progress in quantum computer in the last few years, I think it's reasonable to believe that within 5 to 10 years, there will be a quantum computer which will be able to break RSA, for example. Probably even a bit faster to break the other kind of crypto which is used, which is elliptic curve cryptography, because with elliptic curves, they're actually better in the sense that they have shorter keys, but then they are more it's easier to attack with a smaller quantum computer. So most people believe that the kind of time we are looking at is about 10 years. Okay? In 10 years, there is a good chance that there will be a quantum computer which we can use to damage cryptography. So how do you address these threats? How do you address a quantum threat? We call that quantum safe solution. What can you do to recover safety? You'd have two things, two possible solutions. One is the kind of solution is all the classical solutions, and it's called post-quantum cryptography. So you have to be a little bit careful. Post-quantum cryptography is totally classical. It's using classical algorithms which will replace the algorithm which will be damaged by the quantum computer. So you need to change the mathematical problems. You need to find a problem where the quantum computer, at least today, does not solve the problem. And I think it's very important to know that at the moment, we do have several problems which we believe can be used. And as you probably know, there is a big process at the moment in the NIST in the US. Well, the NIST is in the US, but the process is really all around the world, where people are trying to find the best possible algorithm which will resist a quantum computer. But when you look at them today, you think you find out you don't have a quantum algorithm which will attack them, but it's not absolutely sure that it will not happen in the future. So going to post-quantum is probably a good solution, but you still need to be a little bit worried about how safe is it really. That's why at ID Quantique, especially and in many other places, we advocate to use the power of quantum against quantum, which means that we want to base our new cryptography also on quantum technologies. And here I give you a quick idea about which quantum technologies are available now and will be available in the future. So today you have quantum random number generator. I will talk to them about them a bit further. Of course, quantum key distribution, which we'll discuss a bit more at length later. And that's already available now, which means that today you can use some of the quantum technologies in order to get quantum safe. In a few years, with the evolution of the quantum computer, we will probably have also quantum networks, and maybe in the future, a little bit further down, quantum internet. But I think we don't have time to discuss that at length. What I wanted to show you is that today we have some quantum technologies. in the future, we will have the quantum computer we want to address, and we will also have interesting new technologies using quantum for other purposes. So let's go back first to randomness. What we want now is to be able to generate random numbers, and quantum is the best way to do that, simply because quantum mechanics is intrinsically random. It means you can have a very small system decoupled from the outside world, and if inside you have quantum behavior, then you got intrinsically random behavior, which means that when you use these quantum random number generators, you can keep them isolated. They will still generate random numbers, and they will generate random numbers as soon as they're switched on. You don't have to wait. For example, with a chaotic system, you need to wait for a while. You need to make sure it's really arriving to the chaotic stage. With quantum, as soon as it's on, it's working. The one thing we are using with ID Quantique is by using the noise coming from a beam of light. So I'm not going to discuss that at length because it will take too long. Just going to show you very briefly how it works. We have a light source, and we measure this light source with a sensor. And whatever the light source, there is noise in the sensor. You cannot have a light source which gives, for example, a fixed number of photons in the sensor. It will always fluctuate, and it's coming from the random fluctuation of light itself. There is no way out of that. Therefore, you got an intrinsically random system which will provide randomness. And of course, then what you have to do is to process it. So you got filtering, and you got a lot of things you need to do, because from a physical process to get pure randomness, it's not so easy. But with starting with something which is intrinsically random, you can easily get to a very good source of randomness. And the great stuff about that, which Jean-Sébastien will discuss later, is that you can put all of that in something very, very small, and which requires only a very tiny bit of power, which means that you can put this random number generator in basically any kind of device. And Jean-Sébastien will explain that, for example, with phones. The other thing you can do with quantum is quantum key distribution. Quantum key distribution is a tool in cryptography. It doesn't do anything. It allows you to transfer a key from one point to the other, and I show it on the slide here. You go Alice to Bob, and they want to exchange a message. They will use symmetric crypto, like I show on the slide. But in order to use symmetric crypto, they need to bring a secret key from one to the other. And quantum key distribution will allow you to do that in a very provably secure manner. Again, it would take a long time to explain the details of quantum key distribution, but maybe just in a few words, the idea is to send quantum states, and anybody trying to measure this state on the way between Alice to Bob will modify this state. Here we put the example of soap bubbles. So anybody trying to look at the bubble will basically destroy them. Quantum, you don't destroy them, but trying to look at what's going on will modify the system, which Alice and Bob will ultimately find out. So with quantum key distribution, basically you can be sure that either you share a secret key and you know it is secret, or somehow the transaction has failed and you know it as well, and then you need to restart the transaction and so on. But the great thing is that as soon as you got this key on both sides, you are certain that this key is secret. So what does it give you? It gives you something very interesting, which is that once you use quantum key distribution, there is no time dependence. And I wanted to show this briefly on this graph. If you take any kind of cryptography based on computation, it comes with an expiry date. Let me give you one example. Let's take the Diffie-Hellman. Let me put this. Yep, laser point. Okay. So let's take Diffie-Hellman as a key exchange. We want to exchange a key using one cryptographic process called Diffie-Hellman, which is computational. So at the moment I do my exchange, I need to decide on the parameters. I say, okay, I take this length of the key, I use this kind of numbers and so on and so forth. And what you hope is that this is solid enough to last for a while. But what we know is that the computing power, the computational power is increasing all the time. So obviously, the security of my exchange will decay with time. It's not that Diffie-Hellman is wrong in principle. It's just that because my computing power is increasing all the time, it will become easier and easier to find the key. And basically, for any kind of computationally relevant system, you do have this kind of decrease. Here, what's happening with Diffie-Hellman is that because of the quantum computer, it doesn't go slowly down like that, as it should have done. But now we know that if there is a quantum computer, it will drop much faster. And we know that within 10 years, this will be broken. So we say, okay, let's not use Diffie-Hellman, let's use post-quantum crypto. So we take a new algorithm, and we have the same issue, that whatever we do today, we need to choose parameters which give a good security, but we also know that the security will slowly decay with time. And here, I put the decay which is actually faster initially than Diffie-Hellman, because all these systems post-quantum are not so well known, and there may be new attacks which will decrease the security faster than we expect. So with all this computational security, we know that somehow the security will decrease with time. With quantum key distribution, as I told you, either the key is secure and then it will remain secure, or it's not, and then you don't use it. You know it's not secure and you don't use it. So QKD is really good for high valued information because you want to keep this information. It has a high value and you want to keep it secure for a long time. So it's a good addition to whatever else you can use whenever you have truly important and long life information. So our message is basically that today you got a new threat which is coming from the quantum computer. In order to go against this threat, you need first to generate good keys, strong key generation, which you can use with quantum. And then you have to be agile. You say, okay, for some of the things, I can use post-quantum algorithms because that's much easier to implement. I can use it in different places, maybe for very, very long distance, for example. And in other cases, when I have very important things to transmit, I can use also quantum key distribution. And I would say that in the future, we will have a cryptographic system, which is basically a little bit of both. For day-to-day things, you will probably use post-quantum. And in some others, you will use quantum key distribution. And with that, I think I give the floor to Jean-Sébastien again. What can be done?
It's the fundamental of quantum physics principle that we use in our solutions. A frequent question that we have is why should a company, even with sensitive data, act today? And there is an answer that has been given also by Professor Mosca, is that if you consider the time it takes to migrate existing crypto solution, if you compare this to the lifetime of your data, if you add, I mean, the time to migrate plus the lifetime of the data, you will see that you may need to act already today to be ready in 10 years, even in 10 years, as Bruno was mentioning. And the good news is that already today we propose ID Quantique solutions that can be implemented, and that's, I will give you a few examples. Of course, we have limited time tonight, but don't hesitate if you have other topics that are interesting to you.
Maybe if you mentioned that, Jean, maybe I can add one word here, is that the risk is already today. If today you exchange confidential, I think what is important is to think about the confidentiality. If you today exchange confidential information, somebody could take this information, even if it's encrypted, and keep it, and wait until there is a quantum computer. So what's happening is that you know that the information you're sending today over the internet, for example, might be decrypted within the time of the quantum computer. So if you really have important information and you want to make sure that it's secret for more than 10 years, I think you need now, you don't need to wait. You need to start now to think about how can I send this information in a secure way.
Exactly. Thank you, Bruno. So we'll start with a few examples around the use of our quantum random number generator chip. As I was saying, it has been introduced in the first smartphone. And here, of course, how do you use the QRNG chip output? First, it's fairly simple to implement for developer. There is the Android version, and we are working on the iOS, hopefully. But you, as a developer, can use the randomness output in different application and service. And that is already implemented, especially on the South Korean market, because we launched this phone on the South Korean market initially. And of course, sensitive services, so payment services, crypto services, and cryptocurrency services can use the output of the chip and digital identification services. So we have already in South Korea more than 28 applications running and using the output of our chip. And there are more coming in Europe.
Just before you go on, Jean-Seb, it's interesting because on our slide we don't put the size of the QRNG chip, and I think it's interesting. It looks good. It looks rather big with respect to the phone. In fact, it's about 2 millimeters, as you probably understand. We couldn't put a big thing into the phone, so the size of the QRNG chip is really 2 by 2 millimeters. So it really fits very well into the phone.
Yeah, hopefully it does not impact the size of the phone itself, hopefully. And it's a low power. It's low power. Also, it's important so that your battery can also last long enough. So in Europe, we developed with a partner an add-on on signal application. As you know, there are lots of news today due to the evolution of WhatsApp security policy. Or policy that is bringing more users to Signal, and luckily we worked even before this announcement with creating an add-on. So combining post-quantum crypto and quantum randomness. So you have the best of both sides of post-quantum crypto and quantum randomness embedded and included into Signal, so that we propose a higher encryption level than the default one. And typically today we provide the phone and the application to sensitive organization or sensitive users that want to exchange messages and highly securely.
With something new, which we believe is better. We only add one more layer, and I think this is a recurring theme in all what we are doing at ID Quantique. When we are doing when we do the QRNG, in this application we keep everything. We keep the randomness from the application, the original Signal application, and we add more randomness. When we do QKD, we will keep everything which is below, but we add one more layer to exchange the key securely. And I think it's very important to really make sure that we keep everything. You don't have to replace, you just add an extra layer of security all the time.
Thank you. Another application, so on the another application of the QRNG chip and QRNG usage is combining several chips into an appliance so that we have higher bandwidth and higher output. And then we can feed randomness, for example, to an HSM. That's what we've done here for a customer that generates digital tokens. And this is clearly important to make sure you don't generate the same twice, but even that you have a true randomness source when you generate it. So that's an example. We also feed data centers with Linux server, for example. So there are various examples of using the Quantis appliance in gaming. Of course, in the gaming industry, we use a lot the quantum randomness as well. In terms of phones, there are two phones. I see the question. There are two phones today commercially available. The Galaxy S71, which is renamed A Quantum. It was launched first on the South Korean market last year, and also a VinSmart model, which is a Vietnamese company, but who is now commercializing worldwide. We can give you more detail offline. So other examples of the use of quantum key distribution. So quantum key distribution, as explained by Bruno, is really a safe way to exchange keys and replacing or combine actually with RSA, for example. So as you know, probably classically the keys are exchanged, as mentioned by Bruno, using asymmetric crypto. And the idea of using quantum key distribution is to add a quantum channel. So we exchange qubits and thanks to photons between here in this example data center. So our appliances. So of course you need a physical appliance from ID Quantique that we call, for example, a Cerberus or a Clavis, and you exchange qubits between Alice and Bob on this quantum channel. You need a dedicated wavelength, not necessarily a dark fiber, but if you want to have a longer switch, we usually deploy it on dark fiber. We have also done deployment with doing multiplexing, so that we can combine classical communication and quantum communication. But there is a sensitivity on the quantum channel to be considered. So really the idea is that we have an out-of-band communication for the key exchange. And as you will see later, of course, we increase significantly the security level, because if you eavesdrop the line, you won't see the key exchange, and you won't be able to, even if you breach the RSA key exchange, you won't have access to the quantum key exchange. I wanted to show you an example, a practical example of integration with a leading technology vendor, Adva, who has opened an interface which is based on ETSI proposition, ETSI standard, which is a REST API, so that it can use quantum keys and combine them with their own session key. So the advantage of our solution is that it can be combined with classical encrypted solutions. So here it's a layer 1 encryption solution from Adva, which supports 10 gig or 100 gig. And you don't need to replace, this is a standard solution and standard firmware from Adva. So you don't need to replace your existing, you can plug in the quantum key exchange and quantum QKD to your existing networks. Another example that we have interfaced with is Fortinet with their FortiGate. So here it's using IPsec protocol, and we leverage an evolution of the Internet Key Exchange, which is IKEY protocol, who is used for the key exchange of IPsec. There was a recent evolution proposed by the ITF that allows to use external keys such as quantum keys. And this RFC is from June last year, so it's a recent evolution which now can be implemented into IPsec devices. So simply what we do is we provide the key to the IPsec encryptor. It's a REST API, same interface than before with Adva, and the key is requested with from the Alice side, for example. We provide the key with the key ID, and the key ID is exchanged only between the IPsec devices, and they have simultaneously the same key to encrypt and decrypt. So these are live use case that we've deployed. The first one with ADVA was deployed in Geneva for an electricity company. And as you understand, we are able to, thanks to quantum key distribution, we are able to upgrade existing and enhance existing security solution. It's not only about just the key exchange itself. It's out of band, and it's combined with existing key exchange, so classical key exchange of RSA and elliptical curve. We generate the keys also truly randomly thanks to our quantum random number generator. There's no need to manipulate the keys manually because they are generated randomly and then exchanged over the quantum channel. And the encryptors can decide of the key rotation period. So we can decide typically depending on the line speed or on the volume of data which is exchanged between data centers. We can and the encryptor can define how frequently the key should be updated as soon as there is the enough quantum keys available. But we provide typically we exchange today typically 6 keys per second, which is more than enough to rotate keys quite frequently. We do not work only with Fortinet and ADVA. We also work now with leading vendors, and it has been really a great evolution from last year. Interworking with leading vendors, you see ABB Hitachi, they are present especially in critical infrastructure, utility networks. Cisco, clearly a leading vendor, and Fortinet, Thales. So more and more network vendors are open to accept external keys. Like it's the same concept that we see in the cloud with bring your own key, where we separate the encryption from the key exchange and the key generation. We support now various topologies, so it's clearly data center interconnect is still the most deployed use case and the most simple, but we can go beyond 100 kilometer key exchange and quantum key distribution thanks to a trusted node that will allow like hop by hop communication to extend the reach. And we also map now typical network topologies, because if you need to have the key available in any of the nodes, you need to have the quantum communication happening in parallel. So we support ring and mesh topologies, star topologies, and we deploy such topologies.
Before you go on, there was a question about exactly that, increasing the distance with repeaters. And I think you answered most of it. I wanted maybe to add one more. Today, we use the concept of this trusted node. So basically, you use a link between A to B, and then another link between B to C. And at B, if you want, the keys will appear in the open because they will be transformed into classical things. So that's something we use today, and I think it fits rather well telecom systems, where you do have telecom central in different places. In the future, we did not discuss that too much, but this is the idea of the quantum network, where you will try to exchange qubits from one point to the other directly, and then you don't really need trusted nodes anymore. You need nodes, but these nodes will be non-trusted. But in order to do that, you need to be able to manipulate the qubits in a way which is not truly possible today with quantum memories and so on. But it will be definitely possible even before you have a quantum computer, because it's the same kind of things you are doing in a quantum computer.
Thank you, Bruno. So we deployed other use case. In Geneva, typically we deployed what we called a quantum vault, where we, instead of storing a key centrally in a node, we store the pieces of the keys in different data centers, and the communication between the central node and the remote node is done through thanks to QKD for the key exchange and one-time pad for the encryption. So you have an ultra secure way of storing keys with remote pieces in remote locations. And then you rebuild you can rebuild the key in this example with 3 out of 5 nodes, for example.
Could consider these keys as really the ultimate information, something which requires good safeguard, because basically if you lose your key, you lose your money. So it's very, very important when you do this digital asset custody that you can really recover the key and keep the key for a long time. And the idea of using QKD is again very much in line with the time you need, because you need to keep your key for a long, long time.
Exactly. And so this, we also part of a large project, which is the start of building a European quantum communication infrastructure. Project is called OpenQKD, and we deploy quantum key distribution in many cities in Europe, especially Spain, Madrid, sorry, in Spain, Berlin, Geneva, as I mentioned. And there are more than 40 use cases that are deployed using quantum key distribution in various sectors. So if you want more information, I can share with you offline and discuss eventually a specific use case you would be interested to know more. To wrap up, it's, as you understand, it's important for our customers that have sensitive data. It's important to already acknowledge the risk associated to quantum computers and to act now. There are various steps that could be that can be started depending on the environment, but we discussed the use of QRNG or quantum key distribution. So clearly, it's important to know which data is sensitive and you want to secure. Certainly, high-speed links and sensitive data should benefit from higher security level. So we discuss improving key generation, looking at crypto agility. So clearly, we at ID Quantique also follow the NIST evolution and post-quantum crypto, so that we can use it for key exchange, for example, locally. And many network vendors, of course, are following the impact on existing crypto. So that's an important topic to follow. And on our side, our recommendation is that one size does not fit all. You have sensitive data, you have sensitive links that probably need special care, and that especially would benefit from the use of quantum key distribution combined with classical crypto solution and classical vendor solutions. So that's an overview in a few minutes about our solutions, what we can propose, and how to use quantum tech for improving security. And we'll open the door to questions. So I didn't have the time to filter through them, but
Put limitation for QKD. So yes, indeed. I mean, it's a quantum channel. So depending on how many how fast you can modulate the photons, it will change that. Now we can send something like kilohertz of bits. I mean, kilobits per second, if you want, of keys, of secure key. But remember that the key which is used in symmetric crypto is very small. You need 256 bits, and you can use it to encrypt with symmetric crypto terabytes. So today there is a limitation, but let's say it's not too bad. You can really use QKD for exchanging enough keys to use for a lot of data. Okay, so that's the answer to this question.
Thank you both. We spotted a couple of interesting questions in the chat. I will ask the first one, and then I will hand over to Paolo. So the question was from Brian: which role typically approaches you first, CEO, CTO, or other? We had this a few times where we discussed this quantum security related technologies. So where should the conversation start? At what level? Is it? You mentioned it is the time now to start worrying about this, but where and how should the conversation start?
Yeah, interestingly enough, we see that the discussion can start at different levels. Certainly, it's important in the company to have a strategic vision of how to manage this quantum risk. And so we see, especially in the Fortune 500 large companies, that they have a plan about quantum computer, how to leverage quantum computing, and also how to manage the associated threats. So clearly, this is at the strategy innovation level. There is a focus. Sometimes we have also a specific interest from more operational team, especially when we look at deployment of our solution. Typically, teams, network infrastructure teams that are operating and proposing, ensuring the security level of the network. So it's there is no generic rule, but certainly several layers in the organization can be impacted. Now with the QRNG and especially mobile apps, we have even a wider scope of interest in the organizations. Bruno, maybe if you want to comment here.
One thing maybe we can add to that is the largest network in the world is in China. In China, they've done it a little bit differently. They decided they put a very large network, and it's now covering thousands of kilometers between many cities. And then they ask people to use it, and banks and hospitals. We don't know exactly, but it seems that there are quite a lot of companies using the networks once it's in place. In the rest of the world, it's a little bit different, because also we are talking to companies who want to install for a particular link. So they don't have a big backbone where you can go from one point to very far away, but it's really on a local region where you have a backup center or disaster recovery center, and you want to make sure that if something happens here, 25, 50 kilometers away, you got something else which is still standing. And all the information going from one point to the other has to be protected very, very strongly. This is the kind of customers we can have, let's say, on a more local level. And for this, we obviously talk to CISOs and so on and so forth. But there is these two different ways: a big backbone, and then you can decide to use it or not, or maybe at the company level.
And just building on that, so you're describing, it would sound sort of large banks or other institutions. So they're obviously thinking about it. Similarly, the network vendors are thinking about this. If you're an SME organization, do you feel that maybe they're just not aware of the risks, these smaller companies that may be at threat? Or is there a worry that these small organizations are going to get there too late?
The backbone, if it's there. And for example, of course, I mentioned China, but in Korea, this is what is advocated by SK Telecom, our main shareholder. They want to put QKD in their network in order to provide it as a service. And then, of course, when it's as a service, anybody you want, I mean, maybe you have very secret information you want to keep safe for a long time, but even if you're an SME, if you have innovation, I could think about pharmas, but they're a bit bigger. But anytime you got information which you need to be able to transfer from one point to another today, you could use the infrastructure. If you want to make your own infrastructure, obviously the cost is such today that maybe a small company will think twice. before they can use it. But as soon as you have the infrastructure, the cost is, you need a few keys, so it will not cost much. And one more thing which we didn't say is, of course, you can today think about global distribution by using satellites. We didn't want to mention too much, but if you are in New York and you have some very important data you want to transfer to Paris, for example, today it's not truly possible with QKD, but in the future with quantum satellite you will do that. And there are many, many projects, even commercial ones, going on at the moment.
And back to the SME, so they need to rely on their service provider. Service providers are of course following closely and investing into quantum communication. One example is typically one of the new generation of network is the 5G network, which is secured by quantum communication and quantum security by SKT. But also, for example, we worked with BT. We published a paper together to leverage, if you want, and propose a service level, higher security level on a 5G network for specific usage. So we could imagine, and that's a model we're working on with service providers, to identify that specific traffic you want to secure with post-quantum security and to have quantum safe. And then, of course, as an SME, you need to rely on your service provider, and that's why also we're working closely with service providers.
Excellent, thank you. And that links a bit to a couple of questions that have come up about how people can learn more information. So one of the listeners has said, are there papers that describe the encryption and decryption that's going on in the chip? And then a more general question from James about any advice you have for people trying to understand the quantum cryptography space more. So I don't know, I mean, obviously there's an infinite amount of information on the internet, but is there any particular direction you would point people?
Well, a bit on our website, we have a number of white papers which are not vendor specific, and that already explain, I think, the key principle. Maybe Bruno can comment here. And depending, of course, on the area, then you need to look at different use cases. But at least the principles are described fairly clearly in white papers.
Depending on the level of technical level you want. I could mention, for example, the Cloud Security Alliance. I have to say, of course, that I am the chairman of the Quantum Safe Security Working Group. So I advocate a little bit for what I did, but we did write quite a few papers trying to put it in a relatively simple format. And I have to add that it's not only quantum key distribution, but it's much broader because we do have many people coming from post-quantum. So by looking at what we did, you can have, I think, a fair view of what's going on, including let's say, algorithmic and physical. And both of them are there. So Cloud Security Alliance. If you want to go into more technical stuff, of course, you do have also lots of organization working on standardization, because that will become very, very important soon. Is you cannot use something which is totally non-standard. So people are working on standardizing these cryptographic things, obviously in NIST with standard algorithm, but also in quantum key distribution. So one of the good place to look at is the ETSI, European Telecom Standard Institute. And they have two groups, one working more on quantum key distribution and one working more on post-quantum. So again, you can have a balanced idea of what's going on. Otherwise, as you said, there is endless things. But these few, I think, are relatively vendor agnostic and are trying to get, I would say, a balanced view of what's going on. And of course, you can follow what's going on with NIST. It's, yeah, a little bit complicated.
Fantastic. I'm about to wrap us up. We want to try and finish more or less on the hour. Before I say a final thank you to you, Jean-Sébastien and Bruno, maybe just a few other words to the people listening. So thank you for joining as ever. A few events coming up on the 23rd of February. We have Doug Finker, who is the author of the Quantum Computing Report. He'll be giving us a talk entitled A Tour Through the Quantum Ecosystem. So that'll be a good background for those of you who want a sort of broader background. On the 15th of March, we have Marco Paini of Rigetti and Alexei Kondratyev from Standard Chartered Bank. So they'll be giving an update, Marco on the UK's quantum computer that Rigetti is supplying, and Alexei will be talking about financial services specific applications of quantum computing. And there will of course be our ongoing STAMTish sessions. The next one will be next Tuesday on the 9th. And then we'll also have a number of other coding community sessions. So an awful lot going on. That'll all be available for the usual channels of LinkedIn and Meetup. So thank you for in advance if you're able to attend those. So really it just remains to say thank you to Jean-Sébastien and to Bruno of ID Quantique for your insight, for answering your questions, and for telling us about an increasingly relevant topic, which I think at the moment feels incredibly complicated, but is clear that it's very important and will become something we talk more and more about over the next few years. So thank you for your insight and for your time, and good night.
Thank you very much.
Bye-bye. Bye-bye.